In this problem, we have the state of stress given to us on an element. Sigma x equals 75 megapascals, sigma y equals 100 megapascals, tau xy equals 25 megapascals. And we see that there is a slice with an angle defined in this bottom rightish corner of a triangle, and that angle is defined as 70 degrees. This cut is a little bit different than what we've been using in terms of describing the angle of the cut. What we've been using up to this point is that the cut will usually have a prescribed angle in this upper portion here, and that would correspond to the counterclockwise rotation of the entire element. So when we start to perform equilibrium on the problem, what we're going to say is that the theta is equal to 20 degrees. Now, in question one, we drew this exact diagram, except I've now pulled down the delta A sine theta and the vector for the vectors for representing sigma y, and pulled the vectors for representing sigma x to the left, along with this symbol for this area. Why? Because now in this problem, unlike the one prior, we have a tau xy. The tau xy is 25 megapascals. So how do we handle this tau xy? Well, first we recognize that the tau xy on the left and the bottom face are pointing to the bottom left. So when we draw the tau xy on this triangle that we've been working with, we're going to put them in the same directions as the green arrows here on the original diagram. Now notice I've moved this arrow a little bit to the left as well, and that is to give us a little space to represent two vectors that will sum up to being this tau xy. And you see that this vector right here is in parallel, or is aligned with tau x prime y prime, or the y prime axis, although it's going in the negative y prime direction. And then you see right here, this component is parallel to the x prime direction, but again, it's going in the minus x prime direction. Similarly, we can describe these angles here on the bottom tau xy, or not these angles, but these components of the stress as you see here, and we can also pop in the corresponding algebraic representation for those components. So you see we have a tau xy cosine theta for this component. We already have written out a tau xy sine theta for this component. The angle is in the small portion of these triangles, these right triangles. Well, we can go ahead and further populate this diagram with a tau xy cosine theta, and we can put in a tau xy sine theta here as well. So now we have a complete diagram that we can use to describe the equilibrium and the equations for such equilibrium. So we have the summation of the forces in the x prime direction equal to 0, and the first portion of this equation is exactly what we wrote in question 1, or for question 1. But now we're going to add components with tau xy in them. So we have to look and see that, okay, this is x prime, there's a component here that's parallel to x prime, and there's a component here parallel to x prime. Let's do this one first. So we have a tau xy sine theta, and we go back and we look, and it's acting on the delta A cosine theta face. That's this face. And for the bottom contributing tau xy, we have a component parallel to x prime, tau xy cosine theta, and that's acting on the, where is it, delta A sine theta face. Okay, so we have the delta A sine theta phase, and tau xy cosine theta. And this is going to be equal to 0. For the continuing algebra, we can simplify to have the following equation. All right, and so we have the cosine squared, the sine squared, and those are there. And then we had 2 of these tau xy sine theta cosine theta. For the y prime direction, we can go ahead and copy down exactly what we wrote for question number 1. For the components of stresses that are not associated with tau xy, but then we go ahead and we take a look and say, okay, we have a y prime direction, and we see that we have a minus tau xy cosine theta acting on the delta A cosine theta face, so that's this, and we have a tau xy sine theta. It's acting up, it's just this small portion right here, and that will be on in the sine theta direction. Okay. And then we have a delta A sine theta face, and that we set equal to 0. Rearranging things, we have tau x prime y prime equal to this sigma y minus the sigma x times, or that is in parentheses, times sine theta cosine theta. And then we have our tau xy, and we have a cosine theta squared minus a sine theta squared, like this. So we've algebraically written out the expressions for the sigma x prime and the tau x prime, which is what the question was asking us to do. When we substitute in these numbers, we will get 94 megapascals for sigma x prime, and we will get 27 megapascals for the tau x prime y prime. Okay, I hope this example is helpful. Thank you.